Welcome back to the video course on fluid mechanics. So, in the last lecture we were discussing about the potential flow theories, and then we were discussing about superposition of elementary flows. So, we have seen the elementary flows as uniform flow, source, sink, doublet and vortex, and then we were discussing about the how we can superpose these elementary or basic flows and then get other complex flows which we can use for practical purpose. So, in the last lecture we discussed about the various kinds of superposition like a direct method, inverse method, and then in the superposition process we have seen how we are superposing a uniform flow and then source, how we can superpose to get a half body. So, that we have seen in the last lecture, and also we have seen how to superpose a uniform flow with a source and sink of equal strength with a uniform flow, a combination of source and sink of equal strength with a uniform flow to get Rankine novels. So, this also we have seen from that, say for element from the uniform flow equations, and then say the source and sink equation, how we are deriving the potential expression for potential, and then stream function, and then how we are getting the velocities and various other flow parameters. And then we have seen the after the Rankine novels we have also seen the flow past circular cylinder. So, flow past circular cylinder we can generate by superposition of a doublet with a uniform flow, which we have seen earlier. A doublet is superposed in a uniform flow. So, then with respect to the superposition of a doublet and uniform flow, we have seen that the stream function can be represented as psi is equal to u r sin theta minus k sin theta by r, and the velocity potential phi is equal to u r cos theta plus k cos theta by r. And then the flow past circular cylinder can be seen in this slide. So, here this is the cylinder, and then this is the uniform flow, and then with respect to doublet and the uniform flow we are trying to analyze flow past a circular cylinder, and then we got the various parameters here for the expressions for psi and phi with respect to the potential flow, and then the uniform flow, and then the doublet. So, after that we have seen how to determine the pressure with respect to the Bernoulli's equation. So, with respect to the previous figure here in the slide, say here A is the radius of the cylinder, and then say u is the velocity of the uniform flow. So, then we can use we can find the pressure distribution. Say here, since the maximum velocity occurs on the surface of cylinder at r is equal to a, that means theta is equal to plus or minus pi by 2, Vr is equal to the radial velocity Vr is equal to 0, and the tangential velocity on surface V theta is equal to minus 2 u sin theta, and the pressure distribution is obtained from the Bernoulli's equation. P0 plus half rho u square is equal to Ps plus half rho V theta square, where P0 is the pressure far from the cylinder and u is the velocity far from the cylinder, and Ps is the surface pressure. So, surface pressure Ps we can obtain as Ps is equal to P0 plus half rho u square into 1 minus 4 sin square theta with reference to this figure here. So, this we have seen in the last lecture, and now say as far as since the cylinder is immersed in a fluid, that means flow past a circular cylinder only we are analyzing. So, definitely there will be drag force and lift force acting upon the say the cylinder if we are analyze the real fluid flow cases. So, then if you analyze the flow past a circular cylinder with respect to the superposition theories which you have seen now, the drag force parallel to the direction of uniform flow generally we can obtain as Fx is equal to minus integral 0 to 2 pi Ps cos theta a d theta. So, with reference to this previous figure here, A is the radius of the cylinder, and then theta is mentioned here in this shown here. So, with reference to this we can get the drag force as which is parallel to the direction of uniform flow is obtained as Fx is equal to minus integral 0 to 2 pi Ps cos theta a d theta, and the lift force perpendicular to the direction of uniform flow is obtained as Fy is equal to minus integral 0 to 2 pi Ps sin theta a d theta. So, now the substitution of Ps from the previous expression, Ps is equal to P0 plus half rho u square in 1 minus 4 sin square theta. If we substitute here for Ps, you can see that what we will get is this Fx is equal to 0 and Fy is equal to 0. So, with respect to this figure here, this Fx is in this direction, x direction, and which is the drag force, and Fy is the lift force in the normal vertical direction y, and then Ps is the surface pressure which is acted on this surface like this. So, if you substitute these values with respect to our early analysis, we will get the drag force Fx is equal to 0 and lift force Fy is equal to 0 with respect to the superposition of this doublet and uniform flow. But we can see that in the real case, in the real fluid flow case, this is impossible, since definitely there is lift drag force and also possibility of lift force with respect to, since the there is a flow and surrounding the cylinder, or the cylinder is immersed in a flow. So, there is definitely drag force and lift force. So, this the experience, that is there is a drag on the cylinder when it is placed in a moving fluid due to the viscosity. So, this discrepancy, so when we analyze these kinds of problem with respect to the potential flow theory or the superposition of the elementary flows which we have seen so far, then some parameters are not obtained properly or under predicted, like drag force is 0 here, lift force is 0 here, which is not realistic when we consider the real fluid flow where the viscosity is also considered. So, this discrepancy is called D'Alembert's paradox. That means, when we are using the potential flow theory for the real fluid flow, say like the flow surrounding a cylinder or which we have seen here. So, the drag force becomes 0, lift force is 0, which is not realistic as far as the real fluid flow is concerned. So, this discrepancy is called the D'Alembert's paradox. That means the potential theory, we can see here, it incorrectly predicts that drag on a cylinder is 0, which is not realistic. So, that is what is called D'Alembert's paradox. So, here the reason is obvious, that here we are considering as the potential flow, and then viscosity is not considered, then effectively when we superpose the uniform flow and then the doublet in this particular case, just like for flow past a circular cylinder, it will be all the parameters will not be predicted properly, but as we can see, the velocities and then pressure can be predicted with respect to this superposition of the uniform flow and doublet as far as flow past a circular cylinder is concerned. So, that means when we use this potential flow theory for many of the real flow problems, so we should be very careful which parameter is getting proper accurately or which parameter is not predicting properly. So, we should be very careful while using the potential theory in the case of real fluid flow problems. So, that is very important. So, now with respect to this superposition of potential flows, before completing this, before closing this chapter, we will discuss two numerical examples. So, here we can see, we will first see the superposition of potential flows. So, first example is superposition of potential flow. So, the problem is a source with a flow volume rate of 0.3 meter square per second and a vortex with 1.5 meter square per second are located at the origin. Derive the equations for velocity, potential and stream function. Calculate the velocity resultant at 0.7 meter at the ordinate 0.7 meter. So, here we have got a source of strength of flow rate of 0.3 meter per square second, and then vortex. So, a source and vortex combined superposition of superpose. So, the vortex strength is 1.5 meter square per second. So, we have to derive the equation of velocity and the potential and the stream function and calculate the resultant velocity. So, for source which we have already analyzed earlier, as far as source is concerned, we can derive, we obtained the stream function psi is equal to m by 2 pi theta, where m is the flow volume rate, which is given as 0.3 meters square per second. And then we have also seen earlier the velocity potential can be expressed for say source as phi is equal to m by 2 pi natural log r, where r is the distance to the point which we are considering. So here for psi and phi for source is obtained as psi is equal to m by 2 pi theta and phi is equal to m by 2 pi natural log r. And then also we have seen for vortex is concerned, earlier we have seen for the vortex psi, the stream function can be defined as psi is equal to minus gamma by 2 pi natural log r, and phi is equal to gamma by 2 pi theta. So here this gamma is the vortex strength 1.5 meters square per second, which is given. So now for vortex we have seen psi function and phi function, and m is already given as 0.3 meters square per second, and gamma is equal to 1.5 meters per second. So now as per our superposition theory, since now we are dealing here with a source and then a vortex, so we will use the combined equation. For the combined equation for the stream function will be psi is equal to, so now which we have already seen here, m by 2 pi theta is for psi function. So m is equal to 0.3 by 2 pi into theta. Then we will superpose the for the vortex psi function, which is minus gamma by 2 pi natural log r. So that means psi is equal to 0.3 by 2 pi theta minus 1.52 pi natural log r, which can be simplified as 1 by pi 0.15 theta minus 0.75 natural log r. So now this is the expression for the stream function for the superposed the source and vortex, which we consider in this particular problem. And now the velocity potential is concerned, phi is equal to m by 2 pi natural log r for the source. So m is equal to 0.3, so phi is equal to 0.3 by 2 pi natural log r, and then say the for vortex is concerned, phi is equal to gamma by 2 pi theta. So gamma is 1.5, so plus 1.5 by 2 pi theta, so that is equal to 1 by pi 0.15 natural log r plus 0.75 theta. So thus we get the expression for the stream function and potential function with after the superposition of the source and the vortex expression. Now we want to find the velocity, the resultant velocity. So for that we will just calculate the radial velocity. The radial velocity expression is Vr is equal to del phi by del r. So here if you differentiate this phi function, which is obtained here, on differentiation we will get Vr is equal to del phi by del r is equal to 0.15 by pi r. So similarly we can obtain the expression for the tangential velocity V theta is equal to 1 by r del phi by del theta. So the tangential velocity is equal to 1 by r del phi by del theta. So if you differentiate this function for phi, we will get this is equal to V theta is equal to 0.75 by pi r. So this gives the expression for the tangential velocity. So thus we got the expression for the radial velocity and expression for the tangential velocity. So now the next part of the problem is we want to find the resultant velocity at say 0.77 meters. So x is equal to 0.7 and y is equal to 0.7. So r with respect to the x and y, we can write the position r is equal to square root of 0.7 square plus 0.7 square, that is equal to 0.9899 meter. So that now we can obtain the value of the radial velocity at 0.77 as Vr is equal to 0.77 is equal to since the expression for radial velocity we obtained Vr is equal to 0.15 by pi r. So this is equal to 0.15 by pi into 0.9899, which r is obtained. So this is equal to Vr is equal to 0.04 0.482 meter per second, and then similarly we can find the expression for the obtain the value for the tangential velocity at 0.77. So, the expression for v theta as obtained is 0.75 by pi r. So, 0.75 by pi into r is 0.9899. So, this is equal to 0.241. So, then once we obtain the radial velocity and the tangential velocity, we can obtain the resultant velocity is equal to v resultant is equal to square root of v r square plus v theta square. So, that means here square root of 0.0482 square plus 0.241 square. So, if you take the square root of this, we will get the resultant velocity is equal to 0.2459 meter per second. So, like this. So, here in this particular problem we have superposed a source and then a vortex being superposed, and then we have found the velocity for the expression for the potential velocity potential, and then the expression for the stream function, and then finally we found the radial velocity and the tangential velocity, and we got the resultant velocity at a particular point from the radial velocity and the tangential velocity. So, this is one example with respect to superposition of a source and then a vortex. So, now as a second numerical example, here we will consider a half body. So, as we have seen, the half body which is a superposition of a source and then a uniform flow. So, here the problem is a half body is formed by superposition of a two dimensional source of volume flow rate 2 meter square per second in a uniform flow of velocity 1 meter per second. Calculate the stagnation point and maximum thickness of resulting half body. So, this is the problem. So, here the half body is, as we have seen in the seen earlier, half body is concerned. Here we get a half body by superposition of a source here and then the uniform flow as shown in this slide here. So, here we have superposed here the uniform flow velocity is obtained as 1 meter per second, and then the volume flow rate is for the source is concerned it is 2 meters square per second. So, we want to find the stagnation point and the maximum thickness of the resulting half body. So, this as far as half body is concerned, various parameters, these things we have already discussed. So, here is the stagnation point and then the thickness and all other parameters. So, with respect to the figure here, so we will be analyzing this problem. So, the now we will use the Cartesian coordinate system with respect to this figure here. So, here this figure shows this is the origin, x axis is this direction, and here this is the y axis, and here there is a uniform flow coming of velocity 1 meter per second, and here we have a source of strength 2 meters per second. So, now with respect to this figure we can obtain in Cartesian coordinate system the stream function. So, there is a uniform flow and then the source is there. So, with respect to this, psi is equal to the stream function can be written as psi is equal to u0 y plus m by 2 pi tan inverse y by x. So, here y and x is already defined, y is this direction, x is this direction, and m is the strength of the source, and u0 is the velocity, uniform flow velocity. So, now the stream function is obtained by superposing the stream function for the uniform flow and the stream function for the source, and then this we can write as psi is equal to u0 y plus, so if m by 2 pi is represented by k, then plus k tan inverse y by x. So, this is we can write in this way with respect to this figure. So, this is the velocity potential, equal velocity potential k1, k2, k3 etc., and then we have the streamlines, and the potential line is drawn here for various values. So, now the velocity, the expression for velocity is for u, the velocity in x direction, velocity in x direction is u is equal to minus del psi by del y, u is equal to del psi by del y. So, we can differentiate this expression for the expression for psi. Psi is u0 y plus k tan inverse y by x. So, if you differentiate, u is equal to del psi by del y is equal to u0 plus k x by x square plus y square. So, we get u is equal to del psi by del y is equal to u0 plus k into x by x square plus y square. So, similarly, the velocity in the y direction v is equal to minus del psi by del x. So, that is equal to k into y by x square plus y square. So, thus we got the expression for velocity in x direction and the velocity in y direction u and v from the obtained expression of stream function with respect to the superposition of the uniform flow and source for the half body which we considered here. So, now as per our definition of the stagnation point, this u0, that means the velocity should be 0 at stagnation point as defined here. The stagnation point is shown here. So, for stagnation point u is equal to 0, v is equal to 0. Now, if we use this equation, now with respect to this, if we substitute for u is equal to 0, v is equal to 0, we will get x is equal to minus m by 2 pi u0, where k is taken as m by 2 pi. So, x is equal to minus m by 2 pi u0. So, that is equal to minus m is already given as 2 meters per second. So, this is equal to minus 2 by 2 pi u is equal to the velocity is equal to 1. So, minus 2 by 2 pi into 1. So, this is equal to minus 1 by pi. So, now we want to determine the coordinates of the stagnation point. So, from this we will get the coordinates of the stagnation point as minus a0 or it will be minus 1 by pi 0. So, the coordinates of the stagnation point is minus a0 or minus 1 by pi 0. And the stream function stagnation point with respect to this, now y is equal to say here 0 here. So, we will get psi, the stream function stagnation point is equal to 0 plus m by 2 pi tan inverse y is 0. So, tan inverse 0. So, this is equal to 2 by m is 2. So, m 2 by 2 pi into pi. So, this is equal to 1 we obtain psi the stream function stagnation point is equal to 1. So, now the half body is described by dividing streamlines. So, as you can see, this is the half body with respect to this figure here or this figure here, this is the half body. So, the half body is described by the dividing streamline. So, that we can write psi is equal to m by 2. So, psi is equal to m by 2, that is equal to pi into m by 2 pi. So, that we will get psi is equal to pi k. So, that is with respect to this figure, it is obvious psi is equal to pi k, which we have already seen when we derived all the equation. So, or we can write u0 y plus m by 2 pi tan inverse y by x is equal to m by 2 with respect to the half body, which is shown here. So, then we can write u0 y plus m theta by 2 pi. Now, with respect to this figure, this is equal to m by t, or we will get y is equal to m into 1 minus theta by pi divided by 2 u0, and at theta is equal to 0, we get y max is equal to m by 2 u0, or that which is the maximum ordinate, and at theta by is equal to pi by 2, we get y is equal to m by 4 u0, that is the upper ordinate at origin, and theta is equal to pi, y is equal to 0, which is the stagnation point. So, here with respect to this figure, everything is clear. This is the stagnation point, and y max, y, this is y max. So, all these parameters for this particular problems are clear with respect to the figure. Here this slide, or here you can see that the y max is defined here, and then psi is equal to minus pi k here, and psi equal to pi k here, and all other parameters are already defined. So, maximum width is equal to y max. So, at theta is equal to 3 pi by 2, y is equal to minus m by for u0, which is the lower ordinate at origin. So here the lower ordinate at origin y is equal to minus m by 4 u0. So now the equation of half body becomes u0 y plus m by 2 pi tan inverse by y by x is equal to m by 2, and then maximum thickness occurs as x tends to infinity is the maximum thickness. That means here the maximum thickness with respect to this figure is maximum is this 2 times y max. So that is equal to 1 into y, since u0 is 1 into y plus 1 by pi, m is 2, so 1 by pi tan inverse 0, that is equal to 1. So we get y is equal to 0.5 meter. So maximum thickness with respect to this particular problem is 1 meter here, since it is 2 times y max is 0.5, so 2 times 0.5 is equal to 1 meter. So with respect to this figure, so now we have obtained the, for this particular problem, the superposition, the half body is obtained by superposition of a source and then a uniform flow, and then we calculate the stagnation points and also the maximum thickness of the resulting half body is calculated. So like this, say now we have seen 2 examples for a as far as one is concerned with superposition of vortex and then a source, and then another one is superposition of a say uniform flow, and then the one source is superposed, so that we got the half body. So like this we can superpose various flows, various elementary flows of uniform flow, or we can superpose the source, sink, doublet, or the vortex. So these are the elementary flows and then we can obtain the complex flow phenomena like which we have seen, half body or the flow past a circular cylinder, so like that, or Rankine novel. So like that we can obtain various complex flow condition by the superposition of the elementary flows, and then this can be applied for various practical cases, just like say in a homogeneous isotropic media, like groundwater flow is concerned. In some of the particular cases like this, we can apply this superposition theories to solve some of the complex problem. But as I mentioned, we should be careful that here we are assuming the potential flow theory, so we should be very careful in the use of this superposition techniques, and especially while determining certain parameters like drag, lift, etc. It may not predict it properly, so we should be careful in the usage of this potential theory and then these kinds of superposition. So now this chapter on kinematics of fluid flow, now we will summarize here what we have done so far in this particular chapter. So we have discussed the kinematics of fluid motion. So as we have seen here, we are say not considering as far the particularly the force is concerned, but we are considering various other parameters like velocity field, acceleration field, without giving much attention to the force which is causing the flow, so that the analysis becomes much simpler. And then we also derived, with respect to various theories, we derived the law of conservation of mass, the continuity equation in differential form and integral form. We have derived the equations, and then we have seen how we can apply for various kinds of practical problems as far as law of conservation of mass is concerned. Then in this chapter, the kinematics of fluid flow, we discuss the rotational and irrotational flow, and then as far as irrotational flow is concerned, which is the potential fluid flow is concerned, which is these various applications. We have seen potential theory, we have seen the Laplace equation, how we can utilize with respect to stream function and potential function, and then we have also discussed the elementary fluid potential fluid flows like uniform flow, source, sink, doublet, and the vortex, and finally we have seen the how we can superpose various these elementary potential flows to obtain complex flows, and then how we can utilize to solve various complex problem we have discussed. So, this is the chapter on this kinematics of fluid flow. So, further the next chapter we will be discussing dynamics of fluid flow. So how, with respect to now, so far we are not given much attention to the force causing the flow, but the dynamics of fluid flow, which will be considered next chapter, we will be giving much attention to the force causing the flow, so that we can have the problem become much more complex, and then we will be analyzing it with various fundamental principles of the physics and the fluid mechanics. So, in the video course on fluid mechanics, now we will discuss the dynamics of fluid flow. So, the last chapter we have seen the kinematics of fluid flow, where we did not give much attention to the force causing the flow, but the flow with respect to the potential flow, and then with respect to various other approximations only we have considered. So, now we will see the dynamics of fluid flow. So, as I mentioned, the dynamics of fluid flow is concerned, since we are considering it is very complex, we have to consider all the forces acting upon it, and then on the flow which is causing the fluid flow. So, now in dynamics of fluid flow, the main objectives which we are set here for this particular video course is concerned. First, we will introduce the concepts necessary to analyze fluids in motion. So, as far as dynamics of fluid flow is concerned, and then secondly, we will discuss the finite control volume analysis with respect to which we will be deriving the momentum equation, energy equation, and various other fundamental equations. And then we will be discussing the Euler, Euler, and Bernoulli's theorem with respect to this finite control volume analysis. And then we will be discussing the practical applications of the Bernoulli's equations, and then the inverse momentum theory. And finally, we will be discussing more about the momentum and energy equations and its application with respect to the dynamics of fluid flow. So, now as I mentioned, say the dynamics of fluid flow is concerned, say here we are considering the forces causing the flow, and then we are say as far as the fluid dynamics is concerned, it is the analysis of the fluids in motion. So, as we have seen the fluid statics earlier, there the motion is not considered, the fluid is in is considered at rest. So, here the fluid is in motion. So, we are trying to analyze with respect to say various forces acting, which is due to which the float, the fluid movement or flow takes place. So, we are trying to analyze this fluids in motion with respect to various fundamental principles, fundamental theories, and then we are trying to obtain the various fluid flow properties like velocity, pressure, depth, and other parameters with respect to when the say particular section considered or particular points considered with respect to the fluid movement. So, the motion of fluids here predicted same way as motion of solids. So, as I mentioned earlier, so the fluid mechanics is say most of the theories which we use in engineering mechanics or mechanics of solids are very much valid for fluid mechanics also. So, just like we deal with the solids in motion or the moving solids, so like that how we predict the various parameters like velocity and other parameters. So, like that only as far as the motion of fluid is concerned, we are trying to predict the various parameters very similar to the motion of solid, and then the various fundamental laws of physics and physical properties of fluids we can directly utilize, just like the fundamental laws which we use as far as motion of solid is concerned. Those laws are also very much valid as far as fluid mechanics or fluid dynamics of fluid flow is concerned. And then other than these fundamental laws of physics, we will be using various physical properties of the fluid, which say particular case which we are concerned, the physical properties also will be considered, so that we will be able to solve the particular problem, or we will be able to predict the various fluid flow properties are concerned. So, now as I mentioned, the fluid flow is fluid flow analysis is very complex. Say just like the complex fluid flow, if you consider the spray behind a car or waves on beaches, hurricanes or tornadoes or various atmospheric phenomena like the movement of clouds or the rainfall, all these fluid flows are concerned. All this system is very complex. The movement with respect to, since we are trying to analyze with respect to the fluid flow or fluid motion, the analysis becomes much more complex. So, now for this, all these particular problems are concerned, say we want insight into this fluid motion. Our aim here is we want insight into this fluid motion by using fundamental principles like law of conservation of mass, conservation of momentum, or conservation of energy, and other fundamental principles like Newton's laws. So, that is the way which we are going to approach the dynamics of fluid flow. So, as far as dynamics of fluid flow concerned, say any fluid element obey normal laws of mechanics. As I mentioned, say the laws of mechanics which we are using for solid mechanics concerned, most of the laws are valid for fluid flow is also concerned. So, say since we are most of the time compared to the solid is concerned, we can have a definite shape, and that definite shape only we will be considering in the analysis. But as far as fluid is concerned, we have to since it is continuously flowing, we have to consider, instead of considering the total flow, we may be considering say a particular element or particular control volume. With respect to that only, what happens only we will be analyzing. So, that is the difference between the solid, the analysis of motion of solids and the analysis of motion of fluids. So, now when a force is applied, say we can obtain the behavior of the with respect to the application of the forces using Newton's three fundamental laws. So, these Newton's laws which are as these Newton's laws are applicable to solids movement or motion of solid. So, these are also valid for fluid also. So, as far as the when force is applied, the behavior we can obtain from Newton's laws, three laws. First law is a body will remain at rest or in a state of uniform motion in a straight line until acted upon by an external force. So, this is one of the fundamental principles which we use always in physics and also solid mechanics. So, now this will be also we will be using as far as fluid mechanics theories of fluid mechanics principles, the development of the fluid mechanics principles are concerned. So, the first law is a body will remain at rest or in a state of uniform motion in a straight line until acted upon by an external force. So, if there is only an external force acting upon the body, so here the body means here the fluid, then only if there is no external force, the body will remain at rest or in a uniform motion in a state of uniform motion in a straight line until if there are no external force, it will be at rest or it will be keep on moving. And second Newton's second law is the rate of change of momentum of body is proportional to the force applied and takes place in direction of action of that force. So, this is the Newton's second law. So, here the rate of change of momentum of a body, it's a always say when a force is acting upon, the momentum will be we have to consider the momentum of the body. So, the rate of change of momentum is proportional to the force applied and then takes place in the direction of that force which is acting upon the body. So, this is Newton's second law. So, this Newton's second law is very much used in fluid mechanics principles, fluid mechanics theories. Most of the fluid mechanics theories we are deriving based upon this Newton's second law, based upon which we can obtain force is equal to mass into acceleration and other related theories which we will be discussing further. And the third Newton's law is action and reaction are equal and opposite. So this also we can use in as far as dynamics of fluid flow is concerned. So say the basic fundamental principles, just like Newton's laws, are we can definitely utilize as far as the dynamics of fluid flow is concerned. We will be using these principles to derive various fundamental equations as far as dynamics of fluid flow is concerned. So now we will be looking into what are the different forces acting as far as fluid flow is concerned. So as I mentioned, say this Newton's second law is one of the fundamental law which we will be utilizing to derive most of the equations concerned to dynamics of fluid flow. So as I mentioned, force is equal to mass into acceleration. So this will be utilizing to derive like conservation of mass, conservation of energy, and all these principles. So here the various forces, say, which we say as far as fluid flow is concerned, say here now we are discussing the dynamics of fluid flow or the fluid motion. So when the fluid motion is concerned, the various forces which influence the fluid motion are, first one is the gravity force. The gravity force has got definite impact upon the fluid motion. So first one which we will be generally considering is gravity force, and second one is fluid pressure, based upon which the fluid is moving from one position to another. So second force influence the fluid motion is the fluid pressure, and third is force due to the molecular viscosity within the fluid itself, and then fourth one is the surface tension, say, which is act upon the fluid surface. So surface tension is important, and then the fluid is compressible or if it is incompressible. So the compressibility of the fluid that affects compressible force that we have to consider as far as the fluid motion is concerned. And then lastly the Reynolds stresses, that means forces due to the turbulent fluctuations. The flow can be either laminar or turbulent, which we will be discussing further. So with respect to turbulence, there will be Reynolds stresses will be produced. So these are some of the important forces which influence the fluid motions, just like gravity force, fluid pressure, then force due to the molecular viscosity, then surface tension, compressibility, Reynolds stresses. So all these forces we have to consider as far as dynamics of fluid flow. So depending upon the type of problem which we are considering, or type of equation which we are going to derive, some of the forces will be more important for that particular case, and then others can be the effect will be negligible, and that the negligible forces can be neglected as far as the particular derivation is concerned, or the particular problem is concerned. The important forces we will be considering as far as the derivation of the equation or the particular problem is concerned. So now based upon this, since we are now dealing with the dynamics of fluid flow, the fluid motion, so the fluid motion we can classify into, say, depending upon the how the properties, the fluid flow properties are changing with respect to the motion. We can classify the fluid motion like uniform flow, non-uniform flow, steady flow, or unsteady flow. So this we have already seen earlier. So uniform flow, as we discussed earlier, uniform flow means the velocity is same in magnitude and direction at every point. So if you consider the, say, for example, a channel flow, if we say that if it is uniform flow, if you consider with respect to various sections, say here section 1, section 2, section 3. So here the flow is in this direction, say this is a prismatic channel which we consider here. So for uniform flow means we will say that the flow is uniform for this particular case when the velocity remains same, velocity and other fluid flow parameters like depth remains same in magnitude and direction at every point of the flow is concerned. So that is what is called uniform flow, and so that means means the variation with respect to space, say there is the spatial variation is not there, that means the parameters remains same in magnitude and direction. So that is the uniform flow. But as far as non-uniform flow is concerned, we can see, say a flow is said to be non-uniform. Say whenever, say when we go from this section 1 to section 2, the flow parameters like velocity, pressure, and all these parameters will be changing with respect to space. So the flow with respect to fluid motion, when we consider spatial wise, so the parameters, the velocities, pressure, and other depth, all these parameters are changing, then that is what is called non-uniform flow. And then as far as the third category is concerned, steady flow. So if we say that if the flow parameters are not changing with respect to time, that means the only spatial variation is there. So we say, in that case we say that the flow is steady. That means with respect to time there is no change for the particular fluid flow is concerned. And whenever there is change with respect to, say the velocity is changing with respect to time, say if it is one dimension flow with respect to space and time, or with respect to x, y, z and time, then we say that it is unsteady flow. That means or we call it as a transient flow. So with respect to this uniform flow, non-uniform flow, steady flow, unsteady flow, we can again classify the fluid motion with respect to various characteristics like a steady uniform. So we say that there is no change with respect to space and time, that means it is steady and uniform. So for example, flow in a pipe of constant diameter, so it is steady uniform, you can consider sometimes as a steady uniform flow. And then also we can say classify the fluid motion as steady non-uniform. So that means, say if you consider the flow in a tapered pipe, so if you consider the flow with respect to a tapered pipe like this, so here you can see the diameter is changing from one section to another, so it is tapered pipe. So in this case we can say that the flow is steady non-uniform flow with respect to the definition of the steady flow and non-uniform flow. And then we can also classify the unsteady flow as unsteady uniform flow. That means for example, a pipe connected to a pump, pumping constant rate is switched off. So this is a case of unsteady uniform flow. Or we can have unsteady non-uniform flow, say for example waves in a channel. So these are some of the typical say fluid motion classification, like with respect to how the changes takes place with respect to space, x, y, z axis, the space, and then with respect to time how the changes takes place. So the dynamics of fluid flow, the fluid motion, we can classify accordingly. So now as far as fluid motion is concerned, as I mentioned, there can be also the effect of if any compressible force is acting, then if the fluid is compressible, then definitely the fluid motion is affected. So accordingly we can say that the fluids in motion, we have to consider whether it is compressible or incompressible depending upon the property of the fluid. And then if it is compressible, then with respect to various forces acting, then the properties will change, and then we have to consider whether the flow is compressible or incompressible. And then definitely obviously we have to also consider with respect to the dynamics, fluid flow dynamics or dynamics of fluid flow. We have to consider, say the flow is whether it is three dimensional. As I mentioned earlier, most of the time the fluid flow is varying with respect to x, y and z, but that means three dimension. So but many times we can say approximate the flow instead of, if we consider the flow as three dimension, then it will be the analysis, especially since fluid motion is we are dealing with, so the analysis become much complex. So we can say just simplify the three dimensional flow to two dimensional or one dimensional depending upon the case. So we have to also see as far as the dynamics of fluid flow is concerned, whether we are dealing with the three dimensional flow or whether we are dealing with the two dimensional flow or one dimensional flow. So as we have seen earlier, say for example, say if we consider a river flow is concerned, so large river is concerned. So now if you consider say the two sections say at a distance of 1 kilometer. So this particular case is concerned, if you are interested only what happens in the direction of the flow, if the direction of flow is in this direction, so what happens in this direction, so that this is, even though this river flow is concerned, it is 3-dimensional flow. Depending upon the particular problem we are solving, we can analyze as 1-dimensional flow. That means say in this direction of flow we can consider, so that using 1-dimensional how the variation of the 1-dimensional parameters, since it is more important for this particular problem is concerned, we can analyze it 1-dimensional. Or when we consider a particular section of the river like this here, so what happens in this particular section, then we can take it as 2D. That means it will be say with respect to vertical and with respect to the lateral direction, so maybe Z and Y, so that will be the so Y and Z will be considered here. Or say if you want a complete analysis, we can go for a 3-dimensional analysis. So as far as dynamics of fluid flow is concerned, depending upon the problem which we are dealing, we will be considering 3-dimensional flow or 2-dimensional flow or 1-dimensional flow whenever we need to say approximate or we want to simplify the problem. We will be considering the 3D flow as 2D flow or 1D flow. And then some of the other important parameters as far as dynamics of fluid flow is concerned, we will be considering, since fluid is flowing, so we are considering fluid motion. So the mass flow rate, how much mass is flowing, that is an important parameter. So that we may have to consider in fluids, for fluids in motion. And then volume flow rate, that means discharge Q, that means how much discharge is passing at a particular section or between two sections, how much is the change in discharge. So another important parameter is so called volume flow rate or the discharge. So then with respect to, if you know the cross sectional area, we can say most of the time we will be interested in the mean velocity. So mean velocity can be expressed as V is equal to Q by A, which is the volume flow rate divided by area of cross section. So now further we will discuss about the analysis of fluid flow, that means with respect to motion. So as I mentioned here, when we deal with the fluid flow compared to the solid movement, so here the fluid is continuously say moving. Say if you consider river flow or a pipe flow or any kind of this flow, you can see that continuous movement is, the endless stream of fluid is there. So it is very important that we have to see what part of this stream that we will be analyzing, or that the stream shall constitute the system to analyze. So generally we are dealing with a system, so we have to see which part of that, which one we are analyzing. So as far as solid motion is concerned, that particular solid, how it is moving, we will be dealing. But as far as fluid motion is concerned, we have to see say since we are dealing with an endless stream of fluid, we have to see what part of that will be considered in the analysis. So we have two alternatives generally. First one is we can see the behavior of a specific element of fluid. So here if you consider this particular element, what happens, so that is one approach. So behavior of a specific element of fluid of fixed mass, that means generally we will be considering a closed system, just like a pipe, this particular closed system, what happens. So that is one way of approach. So within that fixed mass, what happens with respect to fluid motion. And second one is define the system to be studied as a fixed region in space known as control volume, through which fluid flows. So generally this will be an open system. So this is with respect to, here you can see a channel flow or a river flow. So we will consider a control volume like this. So between say section 1.1 and section 2.2, what happens. So that is we can define a system of fixed region in space, and then what happens to that, which is so called control volume, and then this is open system. So many of the important fluid mechanism problems we can solve using this finite control volume. So, this is so called we are just defining a control volume, and then what happens to that control volume, that is what we are analyzing. So, many of the fluid dynamics problems we can analyze using finite control volume analysis. Here this finite control volume analysis is much easy to interpret physically, and the usage is also very, we can easily use this concept since it is simple to interpret, and then also the formulas derived from basic laws we can apply directly to the system. So, since we are considering a finite control volume with respect to the fluid motion or dynamics of flow, it is the formula derived we can easily apply to the system which we are dealing with. And then as we have seen, the flow description is concerned, we can either use the Eulerian or the description or Lagrangian description, but here the finite control volume analysis is concerned, we will be dealing with the Eulerian description, and then we will be using the Reynolds transport theorem which we have seen earlier. So, now with respect to this finite control volume approach, we will be deriving the conservation of momentum equation. Earlier we have already discussed the how to derive the conservation of mass equation, the continuity equation with respect to the differential approach and integral approach, that we have already discussed earlier in the kinematics of fluid flow. So, now in this dynamics of fluid flow, first we will be discussing how to derive the conservation of linear the conservation of momentum equation, and then we will be discussing about the conservation of energy equation, and further we will be going for with respect to the dynamics of fluid flow or the fluid motion is concerned, we will be analyzing various problems with respect to these fundamental principles and its basic applications.